Find the volume of the solid whose base is the region in the first quadrant, meaning the top right, and it's bounded by y equals x to the 6, y equals 1, and y equals, and the y-axis, and whose cross sections are perpendicular to the x-axis are semicircles. Okay. So, first thing we're going to do here is draw a picture, which is usually going to be the hardest part for a lot of these problems. So we have, I think, y equals x to the 6th, which will look like this. And we have y equals 1, which will look like that. That's supposed to be more straight than that. That's okay. Y equals 1. That's supposed to be a 6, not a C. And the y-axis, so right there. And the cross sections that are perpendicular to the x-axis, that's the x-axis right there, the horizontal one, they're semicircles. So I'm going to call them half circles. So what I'm going to do then is I'm going to say that we're going to have half circles like this. And this distance here will be the base of the semicircle. So I'm going to draw one of these out over here, get a little bit of perspective. So we have semicircle like this. And we're going to call the top right here, if you look at this, the top is going to be x equals 1, and the bottom is going to be x to the 6th, and there's going to be a little, we'll do a little bit of, this is a terrible perspective. There's going to be a little bit of thickness to this, and that thickness will be, I'm going to call it delta x. So if you see right here, delta x, and we're going to integrate going this direction. So yes, I like that. So there's semicircles, so we're going to do an integral from 0. So y equals 1 equals x to the 6th at 1, 1. So when x equals 1, it'll be the same for both of these. So this point right here is 1. So we'll integrate from 0 to 1. And we're going to do semicircles. The area of a circle is pi r squared, but it's a semicircle, half circle, hemicircle, hemisphere. We're going to divide by 2 and then multiply by delta x. Where I'm using delta x here is just a very small amount. So then I'm going to say that, well, delta x is basically dx. This small amount is basically infinitesimally small. I know it's pretty nuanced. Some people probably even disagree with me, like, that's a silly distinction. Maybe, probably is. And then r is going to be right here, where r equals, it's going to be this distance right there. So we're going to subtract the top minus the bottom. The top one is 1, the bottom one is x to the 6th. But we really don't care about r as much as we care about, oh, no. Other thing, that's the diameter from the top to the bottom. So to get the radius, we're going to divide it by 2. Excellent. We really don't care about r as much as we care about r squared, because that's what we have right there. And so r squared would be 1 minus x to the 6th squared over 2, also squared. So we have 1 minus 2x to the 6th plus x to the 12th. That's just the whole foiling method. That looks pretty good. Is that real? Yeah, I'm good with that. I am good with that. And I'll break it up one more time. So I have 1/4 minus x to the 6 over 2 plus x to the 12 over 4. Okay, so now we can take that, plug it into our equation over here. So we go from 0 to 1, change colors to show that my train of thought is changing slightly. Then we're on a different part of our journey. Pull out the pi. We have 1/4 minus x to the 6th over 2 plus x to the 12th over 4 dx. These are all pretty straightforward. Now they're going to be the power rule. So 1/4 x minus 6x, x to the 7th over 14. So bump the number up, bring it down, plus x to the 13 over 13 times 4. 13 times 4, is that what, 42? I think it's 42. 12, carry the 1, 4, 52. Oh yeah, like a deck of cards. 52. And then multiply everything by pi. And we're going to evaluate this from 0 to 1. Everything has an x in it. So the 0, when we plug that in, oh, different color, 0 will just go away. I know I just crossed out the 0 to write a 0. You understand what I'm going for. So now we'd plug all this in. We do pi 1/4 minus 1/14 plus 1 over 52 times pi. Then we could simplify it, but I'd rather not if you can get away with that simplifying it. So let's look back real quick, see what we did here. So we had a shape here, and normally they say like rotate it about, which gives you a circle, but they said nope, these are specifically semicircles. So we evaluated for each area of our semicircle with a little dx width to it, and that little width gave it a volume. And then we integrated from our starting point 0 to 1. So, yep, I'm confident with this, happy with it, seems reasonable. This is what I would say the final answer would be. Good luck, see you next time.